Section 4.1, we're going to talk about inverse functions. So first of all, let's define a one-to-one function. So a function is one-to-one if each y value goes with only one x value. So we can determine if a function is one-to-one by using the horizontal line test. So it's similar to the vertical line test that we used before to determine if a graph is a function, but instead now we're using the horizontal line test to see if the graph is one-to-one. Okay, so if you can draw a horizontal line that crosses the graph more than once, then it's not one-to-one. Okay, so for example, x squared, which is kind of looks like this graph right here, is not one-to-one because I can draw a horizontal line that touches that graph in more than one point. Okay. All right, so if a function is one-to-one, then it has an inverse function. So the notation for the inverse function, it looks like f to the power of -1 of x. So that is the inverse function of f. Okay. So if you want to find the inverse of a function, you switch the x and the y, okay, or you switch the domain and the range. All right, so which of the following is one-to-one? And if it is one-to-one, sketch the inverse. Okay, so graph A is not one-to-one, so it does not have an inverse. Let's see. Graph B is also not one-to-one, so it doesn't have an inverse. Graph C is one-to-one. So when you have a graph and you want to sketch the graph of the inverse, what I'm going to do is I'm first going to sketch the line y equals x, like as a dashed line right here. So that's the line y equals x right there. Then I'm going to reflect the graph over that line as an axis of symmetry. Okay, so all right, so the points where it crosses that line, those are going to be points on the inverse. So let's say that this graph is f of x. Okay, and I'm going to draw the inverse in red here. Okay, so that red one is f inverse. Okay. Okay, so see how it's like a mirror image. Flips over that line. All right, and then graph D is actually not a function, and it because of the vertical line test, and it's also not one-to-one by the horizontal line test. Graph E is one-to-one. All right, so I'm going to sketch the axis of symmetry, which that's the line y equals x. Okay, now if you'll notice, the graph of f of x is already symmetric to that line. It's already symmetric to that line. So in this case, the function is equal to its inverse. So in this case, f of x is equal to f inverse of x, so that it's the same exact function. It's the same exact graph, okay? All right, and graph F is not one-to-one, so if you draw a horizontal line on top of one of those little horizontal line segments, then your horizontal line is touching that line segment in multiple points all across there. So that's not 1 to 1. G is 1 to 1. So here's my line of symmetry, y equals x. All right, so this line here is f of x, and then I'll use red to draw the inverse. So so there's the inverse. Okay, see the symmetry there? Let's see. Okay, so graph H is not 1 to 1, graph I is not 1 to 1, and graph J is not 1 to 1. Okay. All righty. All right, here we go. Decide whether the functions are inverses of one another. Okay, so again, you're switching the x and the y. So for number 1, let's see. So if I was to make a table for the inverse function of f, I would just take these two columns and just switch them. Just that's all you're doing, is switch those two columns, okay? So all of these x values would move over here to the function value column. And then all these move over here. Okay, so does that match up with this? Not quite, because yeah, no, it doesn't match up. See, it has different x values and everything, so no. So these f and g are not inverses of each other. Okay. Number 2, if we look at that, we can see that those do look like inverses. They're symmetric across that line of y equals x. Number 3, that's going to be a no. Let's say if the blue one is f of x, and then I'm going to use red to try to sketch the inverse of f of x. So it would like sort of look like that. That's what f inverse of x would look like right there, not whatever this thing is. All right, so that's so this one was a yes, and this one was a no. Okay, so it is true that when you take two functions that are inverses of each other and you plug one into the other, it always equals x. So f of f inverse of x equals x, and also f inverse of f also equals x. So what they want you to do on number 4 to determine if they're inverses, plug one into the other. Okay, so f of x is equal to 3x plus 9, and g of x is equal to 1/3 x minus 3. So let's do f of g of x. Okay, so that's going to equal 3 times 1/3 x minus 3 plus 9. And let's simplify that and see if it's equal to x. So if we distribute the 3, so 3 times 1/3 is 1, so that's 1x, and then 3 times -3, that'd be minus 9, and then bring down the plus 9. So -9 plus 9, that would cancel out. 1x is the same thing as x. So that did work. And then we want to check the other way also. So g of f of x. So that's going to equal 1/3 Okay. 1/3 times 3x plus 9. And so let's distribute the 1/3. So 1/3 times 3 is 1. So that's 1x. 1/3 times 9, that would be plus 3. And then bring down the minus 3. So plus 3 minus 3 cancels out, and 1x is the same thing as x. So that also equals x. So in this case, the answer would be yes, those two functions are inverses of each other. Okay. Number 5 says, if the function is 1-to-1, find its inverse. Okay, so, let's see. So this is equal to f of x. So whenever we were looking to see if something like this was a function, we would look at all the x values to see if any are repeated. In this case, we're looking at the y values to see if any are repeated. So we do have 2 y values that are repeated. Therefore, it's not 1-to-1. So therefore, it doesn't have an inverse function. If we were going to find the inverse, we would just switch each of these. So like we would say -8, 6, and then we would say -4, 3, and then -8, 0, and then -3, 5. Okay, but we can see that that is not a function because it's got that and that. So it's not a function. So because there is no inverse function for that. All right. So next we're going to, if the function is 1-to-1, find the inverse, graph them both on the same axis, and give the domain and range of each. Okay, so y equals 4x minus 5. Okay, well, what type of graph is that? Well, that's a linear function. It's a straight line. Y equals mx plus b. So is it 1-to-1? Yes, it is. It's a straight line. Okay, so to find the inverse, we will switch the x and the y and then solve for y. So literally just switch the x and the y. So that would be x equals 4y minus 5. All right, so then I'm going to solve for y. So I'm going to add 5 to both sides. So x plus 5 equals 4y. All right, and then I'm going to divide both sides by 4. So x plus 5 all over 4 is equal to y. So that is equal to the inverse. Okay, and you might want to put that in slope-intercept form. So that would be like 1/4 x plus 5/4 for slope-intercept form, because we're supposed to graph it. All right, so let's start by graphing f of x. Y equals 4x minus 5. That's f of x, let's say. So the y-intercept is -5. Slope is 4, so go up 4 over 1. 1, 2, 3, 4, 1. Okay. Okay, so that's the original f of x. All right, then they want you to graph the inverse on the same graph. So instead of trying to graph this, which if you're doing it on the computer, it might be completely impossible to do it by plotting like the y-intercept and all that. Well, just switch the x and y of each of these individual points. So like this has a y-intercept at -5, so the other one's going to have an x-intercept at -5. Okay. Or you could even think of it like just even make a table of those points that we just plotted for f of x. Because it's got 0, 5, and then it's got 1, -1, and then it has 2, 3, and then just to do the inverse, just switch those columns. Okay, and there you go. You know the slope is 1/4 also, so now that you have that 1 point, you can just go up 1/4 is another option. Jeez, I got my handy dandy ruler right here. Something like that, okay? Lovely. Okay, so in this case, they're both just straight lines, so the domain and range of all of them is all equal to all real numbers. I don't know why my hand likes to put an E on the end of both a lot of times. Alright. Alrighty. Alright, number 7, f of x equals -x³ minus 2. Alright, so f of x is the same thing as y. So we can go ahead and write y equals -x³ minus 2. And then again, we'll switch the x and the y. Just the x and the y, nothing else comes with it. So it's x equals -y³ minus 2. And then we're going to solve for y, so we're going to add 2 to both sides. So x plus 2 equals -y³. So that's like a -1 there, so I would divide both sides by -1. So that would make that -x minus 2 is equal to y³. And then finally just take the cubed root of both sides. Okay, so the cubed root of -x minus 2 is equal to y. So that is the inverse function right there. Oh, and I should have probably started off by saying, is this 1-to-1? Well, yes it is. If you know the basic shape of an x-cubed graph, you would know that it is 1-to-1. Okay. Also, it's going to be all real numbers for all the domain and range for x-cubed function and cubed root. All right. So then we're going to graph. Let's see. So let's see. Let's start by graphing this one. So if we use the parent function for x-cubed, remember back in chapter 2, this is what we did. All right. So the x values are going to stay the same. So -1, 0, 1. And then we're going to take basically the y values and plug them in place of this x-cubed right here. So actually I should, basically put a negative in front and subtract 2. Okay, so that would be 1 minus 2, that would be negative 1. 0 minus 2, that would be negative 2. And negative 1 minus 2 would be negative 3. So that would give us the points to graph this function right here. Negative 1, negative 1, 0, negative 2, and 1, negative 3. All right. So, and you know, if you remember, the shape is like that. All right, so that is your f of x, your original. So then for this one, now all we have to do is just switch those. So for the f inverse, just switch the columns. So again, negative 1, negative 1, negative 2, 0, and negative 3, 1. And then again, remember the shape, it's a cubed root. And you can also know that it's supposed to be a reflection. So it's a reflection over that y equals x line. So this line. Beautiful. All right, and so as we can see, everything's all real numbers, domain and range of both, without an E on the end of the word both, is all real numbers. Okay. Number 8, same thing. So this is a rational function, which we just went over how to do this in section 3.5. So if you want to make sure if it's 1-to-1, we could go ahead and start by graphing this. So it would have a vertical asymptote of x equals 0. And then the degree on the bottom is bigger, so that's big on bottom, 0 for the horizontal. So horizontal asymptote is 0. And then it doesn't have any x-intercepts, and it doesn't have any y-intercepts either, because the numerator can't equal 0 and the denominator can't equal 0. So if we did a little table though, let's say we had, if x is equal to 1, 4 over 1 would be 4. So there's a point we can plot. So there's that. And if we said x is equal to -1, 4 over -1 would be -4. So there's another point we could plot. Alright, so there's our graph of f of x. So now we can see that it is 1-to-1, so it does have an inverse. So we've got that graph already out of the way now. And I'm going to go ahead and switch the x and the y so I can calculate the inverse. So x equals 4 over y. To solve for y, I would multiply both sides by y. So basically x times y is equal to 4, and then to get y by itself, I would divide both sides by x. So y equals 4 over x. So that is the inverse. So this is a case where the function is equal to its own inverse. So I should have drawn this in purple because it's red and blue on top of each other. All right. And domain and range are all, well, no, let's see. Actually, the domain is everything besides 0, and so is the range. And same for both functions, since both functions are exactly the same. So domain and range of both is equal to -infinity to 0 union 0 to infinity. Okay. Number 9, also a rational function. So let's see. In this case, you would have a vertical asymptote at x equals 2. You would have a horizontal asymptote. Exponents are the same, divide coefficients. So that's y equals 1. X-intercept, set the numerator equal to 0, so that's going to be -4. Y-intercept, plug in 0 for the x's, so 4 over -2 is -2. Okay, so let's graph that. Okay, that makes sense. All right, and we don't have any other x-intercepts, so it would have to be up here. Let's see. I could just draw it randomly, but I feel like I should have a point or two. Let's say if x is 3, that's going to be 7 over 1, so that's going to be 7. Can I fit that on here? Probably not. What about if x is 4? That'd be 8 over 2, so that'd be 4. That would work. I can plot that. All right. What about 5? That'd be 9 over 3, which is 3. So that's right there. Okay. That's good. Yeah. Perfect. Alrighty, let's see then. So we can see it's 1 to 1. So it does have an inverse. Okay, so we've got y equals x plus 4 over x minus 2. So we're going to switch the x and the y. So y is going to go in place of both of those x's. So it's going to be x equals y plus 4 over y minus 2. So then, I shouldn't have put that so close to the edge over here, because we got to multiply both sides by y minus 2. Okay, so that will cancel that out. So I have x times y minus 2 equals y plus 4. And then I will distribute the x. So that'll be xy minus 2x equals y plus 4. So I am trying to solve for y, so I need to get all the y's on one side and then everything else on the other side. So I'm going to subtract y from both sides, and I'm also going to add 2x to both sides. All right. So then I'm going to have xy minus y equals 2x plus 4. Okay, now what I need to do is factor out the y. There's a greatest common factor of y over here. So when I divide that out, I'll be left with x minus 1, because y divided by y is 1. So y times x minus 1 equals 2x plus 4. Okay, and then finally I need to divide both sides by what's in the parentheses, which is the x minus 1. So y equals 2x plus 4 over x minus 1, and that is my inverse function. So basically, to graph that, all I have to do is just everything from the original, just switch everything. I could just go through all the same steps, but just switch everything. So like in this, so like switch the vertical and the horizontal, switch the x and y intercept. So for the inverse function, you're going to have a vertical asymptote at x equals 1. You're going to have a horizontal asymptote at y equals 2. You're going to have x-intercept -2, y-intercept -4. And if you check, you'll see that that does make sense. Okay, vertical asymptote. This is going to be kind of a lot for this one graph, but we can do it. My videos about